Our video is on how to find the velocity and acceleration with displacement being given and using calculus to find these equations.
We hope you learn what displacement, velocity, and acceleration means, how to use power rule, and what this means in the real world.
These are the definitions of displacement, velocity, and acceleration. Displacement is the directed distance of an object from a given reference point at a given time. Velocity is the instantaneous rate of change of displacement, and acceleration is the instantaneous rate of change of velocity.
Displacement and velocity are unique because, unlike distance and speed, they have direction.
To use the power rule, you take your primary function, which in this case it would be f of x equals x to the n power, and to get the derivative of that, you would multiply n by x and then subtract your power by 1. So I got the derivative by bringing down the exponent and multiplying it by x, and then subtracting the original exponent by 1. So my final derivative would be 3x to the second. So our original function is 7x to the negative fifth. So we take the exponent and multiply it by 7, which you would get negative 35, and then subtract the exponent by 1, so you'd get negative 6. So your final derivative is negative 35x to the negative 6th.
Because we have the displacement equation, we can also find the velocity and the acceleration using that equation. The way we do this is by finding the derivative of the displacement equation. The first derivative of the equation will give you the velocity. You can find the acceleration by taking the derivative of the velocity equation that you just got. This is also called y double prime because it is the second derivative of this displacement equation.
So your first equation is the displacement, and you're trying to find the first derivative, which is the velocity. So you take the exponent and multiply it by the 9, and then subtract 1 from the exponent and you get 1. Then you take the exponent of 30t, which is 1, and apply it to the 30, and you'd get t to the 0, which is just 1, so the t cancels out. And because there's just a number with no variable at the end, it just becomes 0. So your first derivative is 18t to the first power minus 30. Now in order to find the second derivative, which is acceleration, you apply the power rule to your first derivative, which is velocity. So you take the power of 1 and multiply it by 18, and the t becomes t to the 0, which is just 1, so it cancels out. And then 30 is just a number, so you cannot apply the power rule, so it just becomes 0. So your second derivative will equal 18. Your given displacement is y equals t to the fourth minus 11t cubed plus 38t squared minus 48t plus 50. In order to get your first derivative, you apply the power rule to get 4t cubed minus 33t squared plus 76t minus 48. Then to find the acceleration, you use the power rule on the first derivative to get 12t squared plus 66t plus 76. With every derivative, the exponent decreases by 1 in each term, causing the last term in each equation to become 0.
This graph shows the equations of the displacement in red, the velocity in blue, and the acceleration in green. One of the most important things to take away from this graph is the difference in curves. As you may know, the number of curves in a graph is determined by the highest power exponent in an equation, minus 1. So, for the displacement equation, where the highest power is 4, we have 1, 2, 3 curves. When we take the derivative of that equation, the graph only has 2 curves, as the exponent goes down by 1 when you take the derivative. The last graph only has 1 curve, which fits the pattern of graphing the derivative. The math behind displacement, velocity, and acceleration are what form the basis for the existence of the laws of physics. Scientists, astronomers, physicists, and many others use this math consistently in their jobs. This math is specifically used when scientists send a rover to Mars. In order to land properly and safely, the computers in the rover must perform thousands of calculations a second. This is done through the use of many sensors outside the rover. These sensors can tell how far away the rover is from the surface of Mars, which, in turn, lets it calculate its own velocity and acceleration and report it back to the scientists. The computers in the rover does this using a similar process to how we find the velocity and acceleration in this video. The rover knows its displacement through its sensors. It then calculates velocity and acceleration and makes changes to its trajectory based on what it gets. This process helps it land safely on Mars and make many discoveries in the future.
We chose this topic because in every unit that we've covered so far, we have to find derivatives. This is one of the first derivative rules that you learn, and it's important to understand because it builds the foundation for learning other derivative rules.
Reinforcing something fundamental like the power rule is always useful because it makes sure you don't forget about the small things when you're working with much more complex problems. Just like everything in calculus, this rule is built on top of again and again, so it's important to have a strong foundation at the bottom of your knowledge.